This is the first question. This is a planning question. This is about determining the relative molecular mass, MR, of a small sample of a volatile liquid. Volatile means a low boiling point, so boil easily, by measuring its mass, so the mass of the volatile liquid, and then you heat it to vaporize it, so liquid to gas, in order to obtain the volume as a gas. So you want the volume of the gas, but you want the mass of the liquid. So this is mass of the liquid, and then this is volume of the gas. So very important to think about not just volume, not just mass, but you got to specify what is what, because it's important that way. Okay, so they say the mass of the liquid because it's difficult to measure the mass of the gas, but if all the liquid goes to gas, then your mass of liquid is equal to mass of gas. And that is why when we have the ideal gas equation, PV equal to nRT, you can rearrange that. So the N refers to the mole of the gas, so that is the mass over the MR of the gas. Then rearrange it, you get MR of the gas is mRT over PV. And equation don't mean anything unless you specify their definitions, their meaning. So M equal to the mass of the liquid, which is equal to the mass of the gas, because you do not lose any mass when you convert from liquid to gas, because there's just boiling or vaporization. You do not lose any mass at all. Okay, it's a physical change. R is molar gas constant, and then the rest are all the usual definitions, but we'll just write all of them down because it's important to know what we're talking about. Yeah, so P equal to pressure of the gas, and finally V is the volume of the gas. And bear in mind that because the MR will be in gram per mole, the mass of the gas will be in gram, all right, whereas this one is in joule per mole Kelvin. This one is in Kelvin. So this one is given in the data booklet all the time, but you don't have data booklet in paper 5. Does not mean that you shouldn't know what you're talking about, all right? Pressure of the gas will be in Newton per meter square or Pascal, and the volume of the gas will be meter cube. All right, not that they asked for it anyway. So the next bit of the question. The volume of the vaporized sample depends on temperature and pressure. So in this experiment, you have a volatile liquid, which the mass, you vaporize it, and then you record the volume. So you have the pressure correctly recorded as 101 kilopascal, but the temperature was incorrectly recorded as 50 degrees Celsius, and the correct temperature was 60 degrees Celsius. Bear in mind that despite them giving you the data in degrees Celsius, because of what we actually know from the ideal gas equation, the temperature is in Kelvin. That's why it's important to bear in mind that what is what, right? Okay, so if this is in Kelvin and these are in degrees Celsius, so you do not just use degrees Celsius straight into the ideal gas equation. You have to convert them to Kelvin. All right, and then you need to consider the effect of this different temperature on the gas volume. So that is your Charles' law. I hope you know what Charles' law says. The volume of a gas is directly proportional to the temperature of the gas in Kelvin at constant pressure. All right, so that is Charles' law for you. So how okay would the value of the MR be affected? Okay, so first of all, the correct temperature is higher because it's 60 degrees Celsius. So the correct temperature of 60 degrees Celsius is higher than what was recorded, than the recorded temperature, which is 50 degrees Celsius. So Charles' law, so I'm just stating the effect, right, which is basically, if you just say Charles' law, it doesn't mean anything at all. Okay, so Charles' law states that volume of a gas, for a gas at constant pressure, Okay, so you need to think about what is constant, okay, and then what is changing. All right. The volume of a gas, I can use this sign, directly proportional to the temperature of the gas in Kelvin. All right. So I've just stated those things, but what is the effect then? Okay, therefore higher temperature of 60 degrees Celsius means greater volume of gas in reality, okay, not what they are recorded. So in reality, so what can we say? So you need to compare the calculated MR for 50 degrees Celsius versus 60 degrees Celsius, right? I started by saying the one with higher temperature would mean greater volume of gas. So if you go back to the equation, MR equal to MRT over PV, MR equal to MRT over PV. So at higher temperature, so following on from what I just said previously, so greater volume of gas, and so we expect the MR to be lower despite the temperature being higher, because we already take into account that, you know, temperature and the volume of gas can change. If you want, you can compare the two. So what am I saying? What I'm saying is that you have MR is proportional to the temperature over the V, which is at 60 plus 273. Okay, and let me think. The temperature itself is proportional to that, so maybe I shouldn't be thinking about that at all. Hang on, let me think through this problem first. So Charles' law says that for a gas at constant pressure, volume of a gas is directly proportional to temperature of a gas in Kelvin. Okay, so if my temperature is higher, my volume is higher. So if my volume is higher, my MR will be lower. So therefore the MR for 60 degrees Celsius would be lower. I think that should be alright. Let me think. I think so, yeah. Actually, I think I can make it sound a bit better. Okay, so this is the actual temperature, but this is what you have incorrectly recorded. Okay, so this is your reading. Okay, but so this is your reading at 50 degrees Celsius, at 60 degrees Celsius, but you have incorrectly used 50 degrees Celsius, so that is the incorrect thing. But as a result of the actual temperature being 60 degrees Celsius, your volume is actually bigger than what it should be. If the volume is bigger than what it should be, the MR will be lower. Okay, so maybe I should say at actual higher temperature, since the volume of gas is greater, then the MR will be lower. So I think there's a confusion between this question actually, and I was a bit confused at that time. I mean, when I first started this question, was that this is the temperature you have used for your reading in your equation, but in reality it's actually higher. So in reality the volume is higher, and therefore the MR is actually lower. Okay, so I hope that makes sense then. So next question. So you maintain the temperature at 60 degrees Celsius, which is the actual temperature, but you increase the pressure. So this is the new change. So previously it was 101 kilopascal. So from 101 kilopascal to 110 kilopascal. Would this have an answer that was nearer to the true value? Explain the answer. So this is a different type of scenario. State and explain. It's basically the same kind as the previous question. All right. So at constant temperature, so we know at constant temperature, when pressure increases, the volume of gas decreases. This is actually Boyle's law. Okay, or you can say PV equal to constant for gas at constant temperature. So at constant temperature. So what do we know so far? So when your pressure is increased, your volume of gas will actually decrease. Okay, your volume of gas will actually decrease. So volume of gas decrease would be the opposite of that, and that would mean the MR would be higher. So the fact that this was one mistake and this didn't follow through from that mistake. But then we also have to remember that this is only true where your system can change the volume, can expand and contract at the same time. But what we have in this kind of setup is that you have a fixed container to hold the volume of the gas, which means that the volume doesn't change, and therefore we are not essentially just looking at Boyle's law on its own. So when we just increase the pressure here, the volume of the gas doesn't exactly change because you are not in a balloon which can go increase in volume or decrease in volume. So that's why I was a bit in a bit of a dilemma, because where the PV is equal to constant, that means there will be no change. But we really need to be thinking about the change as well as the system that we are in at the moment. So when pressure increase, so the volume will remain the same, because the volume of the container doesn't change. It's the container itself that holds the gas itself doesn't change. So from the equation itself again, so MR equal to MRT over PV. So it relates to the previous question, as this is part 2, but whatever change that was here, it's not essentially the change that is given in this question. So when pressure increase, and therefore the MR will decrease. When pressure increase, then the MR would decrease. Is that true? Let me see. So as the volume of gas decreases, we can see that it's the opposite effect to what we saw in the previous question when we had higher temperature in reality. So when you have lesser volume of gas, that means that the MR would be higher. So the lesser volume of gas, therefore the MR would be higher. So that is actually answering the first part of the question, as the second part of the question, which is explain your answer. But we haven't really stated the first part of the question yet. Would this have an answer that was nearer to the true value? So previously we have the MR that would be lower, and here the MR would be a bit higher. So in reality, so this give nearer value to the true value of the MR. Okay, so in this kind of question where you state and explain, or where they ask you something and then explain, you gotta consider that you need to answer each and every bit of the question. So even though it's only 1 mark, so that's why I went back and numbered them, so you can see exactly that there are how many different parts of the question that you need to fulfill, okay, before you move on. All right, and it's something that a lot of students are very complacent about, and they don't bother, because you not necessarily have time to check back your work, so you should check them as you go along each part. So this is the experimental design bit. When you determine the MR of hexane, the boiling point is 69 degrees Celsius, so that is lower than the boiling point of water. It's actually quite low, but it is a liquid at room temperature and pressure, because room temperature and pressure is 25 degrees Celsius, 298 Kelvin. So you have a Victor Meyer tube that you can use. You have a long tube, you have a bulb at the base, in which you can vaporize the sample. So this is the bulb at the base. You have the liquid, I guess, and then it will get vaporized. All right. So what do we know here? The tube is surrounded by another, which can be used to heat the content of the first tube. So I think this is the small sample tube that is put inside. Inside where you heat the outer bit, and then it will vaporize the inner bit, which will vaporize the hexane with the low enough boiling point, and when we vaporize the liquid hexane, it's going to go into a gas. And as part of your measurement, you wanted to measure the volume of the gas, so this is about a gas collection apparatus. All right. So a small sample tube is inserted at the top of the Victor Meyer tube. So yep, okay. And then that small sample tube is small enough to fit inside the Victor Meyer tube. You fall onto the free sand, which is hot. Okay. The sand will cushion its fall because you're putting glass into glass, so you don't want the glass to break. Okay, so the stopper is then replaced. You need a stopper because you do not want the gas that get vaporized. You don't want it to escape out the top, because then whatever gas that you collect, the volume won't be accurate then. Okay. The hot sand causes the hexane to vaporize. It expels the air contained in the Victor Meyer tube. So how the apparatus should be heated, so that's the first bit. And then you gotta allow the air to be expelled, so that means you need the air to be expelled, and then you can collect and measure the sample of hexane. So there's bound to be a bit of air inside, and as the hexane get vaporized, the gas will push against the air, and the air will be collected as well. So it's all part of the gas collection apparatus. Hexane is insoluble in water because it's a non-polar organic molecule. So what I'll have is, I don't think that thing is very well drawn, but anyway, so I will have my graduated measuring cylinder, which is not the most accurate thing in the world. And if you want really accurate stuff, you can use a pipette if you want to. But we're just doing gas collection, and if you have done any practical experiments involving gas collections, you would know that we can sometimes use graduated measuring cylinder to collect gases as well. All right, so there's your gas collected inside, and then this is just your water bath. Well, it's not a water bath, it's just a water basin. Okay, because we are not heating it. All right. In fact, I think any suitable gas collection technique or apparatus would be okay, because like I said, you might be thinking about using pipette, which is far more accurate and it's entirely acceptable as well. Okay. How would we heat this one up? So this is glass, right, and we want to heat up the sand. So I assume that we are not going to put a fire here, because inside here will be air, and then air is a poor conductor of heat. So if you heat here, and glass is a poor conductor of heat as well, so you got to heat the glass and the air. Not a lot of heat is going to reach the sand, so you don't want that. So perhaps we can have water, and then you can have water bath to heat up the sample. And we know that we can use water bath to heat up samples in glass tube or in beakers or whatever, because they are quite safe. Yeah. So how the apparatus should be heated, like a water bath, which is all right. How you're gonna collect the gas, which I just did with a collection over water there. So my connection should have been a bit better, but anyway, that's the best I could do. Suggest one hazard. So usually with hazard thing, right, they will give you a table telling you about hazard, like what are the hazards associated with it. But hexane is one of those things, right? It's a petroleum product. It's a hydrocarbon, C6H14. And you should know, as with all petroleum product hydrocarbons, they are extremely flammable. Okay, it is extremely flammable. So you do not put a naked flame near a flammable liquid at all. Okay, so keep away. No, actually they don't say what are the safety precautions, so I do not need to say keep away from naked flame. In fact, they just want you to talk about the hazard. All right, so it is a flammable liquid. You can probably talk about the breathing associated breathing problem as well. As with all the petroleum products, you do not want to be sniffing around petroleum products. Now, they don't smell good when you go and fill out petrol at all. Okay, so carcinogenic in the long run, but carcinogenic is not an immediate effect, so it's not an immediate hazard. All right. With the gas collection apparatus, so they kind of give you the hint there. So you need a gas collection apparatus. You do have expel air. So in addition to whatever volume of gas that you are collecting, you do have a bit of air that you'll be collecting at the beginning as well. And that is what this question is. Will be collected before the hexane is introduced, meaning to say before you actually start gathering the volume of hexane, you will actually collect a bit of air as well. Yeah, okay. So why is this? So at high enough temperature, at high temperature, I guess, whenever you heat gases up, air can expand. All right. And as you know, like there's a principle of hot air balloon anyway, right? You heat up the air, and then if it makes the balloon go big, and then it will float up because of the pressure exerted against the outer pressure resulting from the hot air. Yeah, okay. So air expands, and this rises up the tube and gets expelled first into the gas collection apparatus. As you can imagine, the air itself is already gaseous, but your hexane is still a liquid. So which one do you think will be easier? The expansion of the gas, the air, which are already mixture of gases, or will it be the vaporization of the liquid hexane, which involve breaking the weak van der Waals forces again? All right. So at which stage should the sample tube be dropped into the Victor Meyer tube? So you want it to heat up, right? So as you know that that you will have a bit of air inside, and you need to collect that first reading, and for as long as you still have air, or the gases that are being present, they are being expelled, you will keep on seeing bubbles there, and then you will record the reading, because whatever volume that is, there is your initial volume reading, because whatever there is there will just be air without any hexane, because you haven't dropped any hexane in. So that's your first reading. So when you drop the hexane in will be when there is no more movement of this reading. That is a result of no more bubbles of the air being expelled. So that is when we can drop the hexane in, and then we can start reliably measuring the volume of hexane vapor being given out. All right. So at which stage? So when no more air is being expelled into the gas collection apparatus, and you can tell this as indicated by normal bubbling, because it's quite hard to read on the graduated gas syringe or graduated measuring cylinder or burette, but should be able to tell by just looking at normal bubbles of gas as you collect it over water. Yeah, normal bubbling of gas being collected over water. But again, these are all just experimental observations and techniques that you would have known anyway. Okay. Only then you add the hexane. Okay, when normal air, only then we add the hexane in that small liquid vial, yeah, into the hot sand. Okay, this is the last bit of this planning question. It's for 3 marks, which means quite a bit of things that they want here. They want measurements, so it's plural. You need to make measurement in order to determine the relative molecular mass of hexane. So just now remember that MR is MRT over PV. So what do we need to measure? Okay, so we need to know how much mass of hexane have been evaporated, right? So remember just now at the very beginning, so the mass of liquid is the same as the mass of gas, but we can't, it's very hard to measure the mass of gas, and because we know there's no change of mass when you vaporize something, conservation of mass theory. Yeah, so we need to know the mass of the liquid, and the liquid is inside a small sample tube with a hexane. So if you know what is the mass that you put in, the tube plus the hexane, and you have the mass of the tube at the end. Okay, that is the difference will give you the mass of the liquid hexane being burned. All right, so the first one is to do with the mass of the hexane being burned. So it's the mass of tube and liquid hexane. And then the second one will be the mass of empty tube. Okay, so after all hexane has been vaporized, so either at the end of the reaction, okay, I mean at the end of that vaporization experiment, yeah, okay, so the difference between these will give you the mass of hexane, the mass of the hexane vaporized, okay, and that is not what you measure, because that is what you calculate from two different mass measurements. All right, and what else do we need? So we have the mass, the molar gas constant is constant, obviously, and we also need the temperature. So the temperature of the hot water bath, which is assumed to be the temperature at which this thing will happen. Of course, it will need to be higher than the boiling point of hexane, otherwise the hexane won't vaporize, right? If it's just water at room temperature, the hexane won't vaporize at all. Okay, and then the fourth one will be the pressure. So you need to know the pressure of the system, the pressure of the gas. Okay, and lastly, you will need to measure the volume of the hexane gas being produced. But remember that they already kind of guided you that you already have a bit of expel air, so you don't take it from zero. So you need to take it from the moment when there is no more bubbles being produced before you add in the hexane vial into here. So that is your initial reading. So that's the volume of the the volume reading before hexane was added. And of course, then as the hexane get vaporized, this volume will increase again, and this level will fall down, and then you have the volume reading after hexane was added. Okay, so you will have the volume reading on the I guess graduated measuring cylinder, or burette, or gas syringe. I mean, which depending on whichever one you use, gas syringe or burette. Before hexane was added, and then after hexane was added, basically the vial containing the hexane was added and completely vaporized. So until no more gas is being collected after all the hexane has been vaporized. All right, so that marks the end of this first planning question, which is not for this next question, question 2. It's a data analysis question, evaluation analysis question. So you have various masses of solid barium hydroxide, and you have hydrochloric acid, and you contain a polystyrene carb. So this is about calorimetry. So you must have done this kind of experiment before. This is about a strong base and a strong acid. So this is most likely about enthalpy of neutralization, which is part of your AS syllabus under enthalpy changes. So in each experiment, you have a fresh sample of the acid, and you measure initial temperature as you would normally do in a calorimetry experiment. After you add the barium hydroxide, you stir the acid because you want to ensure a uniform mixture of the acid and the base, and then you reach a maximum temperature. So this reaction is exothermic, as you would know from neutralization. It's just H plus OH minus give you H2O. So involve the recombination of the H plus and OH minus to form the new covalent bond, which is OH covalent bond, without breaking anything because they just come together. Oppositely charged ions by electrostatic, they form the covalent bond, and therefore is exothermic. and that's why you get a maximum temperature reach, because enthalpy neutralization is exothermic, never endothermic. All right. So results of the experiment are recorded in the table below. You need to complete the table to give the temperature rise. So temperature rise is actually delta T, not T. All right. Barium hydroxide added in mole. Okay, so you're not given any periodic table in paper 5, which is why they already given you all the information here. So this is telling you the MR of barium hydroxide. So the mass of 1 mole of the substance is, well, the molar mass, gram per mole. That's what they're saying. The mass of 1 mole of that is gram per mole. So what do we need? We need the amount to 3 significant figure, but we need the temperature rise to 1 decimal place. So this kind of thing are very important not to lose marks on, and it's only 2 marks. And I've gotten my calculator. Well, I've dig up my old calculator back again, having lost my newer calculator recently. But anyway, still know all my old calculator. So the initial temperature is there's the maximum temperature reached. So 22.2 minus 21.0. Get 1.2. 2.4. So this kind of thing takes time, yeah, and do not think that it's just a matter of keying in a calculator and stuff. I would highly encourage you to actually time yourself and see how long you take doing all this without making any mistake at all. And this includes the next bit, which is plotting of graph, because it takes practice actually, and if you don't believe me, you should, if you've never done a paper 5 before, you should try and see how long it takes you, because why are they the same? Have I done something wrong? Nope, they're the same. What I'm saying is that the same skill set is also essential for your so the next bit, which is the mole, is just the mass over the MR. As I was saying, the next bit, drawing graph, is also essential in all your other sciences as well, depending on which sciences you take. Yeah, paper 5, alright? I'm sure they involve drawing graph as well, yeah? 585, so this is the one that I had to convert, because it's as 0.005847, so 3 sig figure. 1.50 divided by 171, 0. .0117. This is another one I had to run it up correctly. Okay, so that's the last bit of it, and now unsurprisingly they want you to plot a graph to show how the temperature rise varies with the mole of barium hydroxide. So unlike the usual calorimetry kind of diagram where it's temperature against time, this is different because it's temperature rise, which is this table here. So this is the y-axis, because y-axis against the x-axis. So this is the dependent variable. So if you watch my other 5 tutorial video, you would know that I credit this friend who taught me this very catchy phrase, that why are you so dependent? Why are you so dependent? So the y-axis is the dependent variable. Okay, it's the one you measure as you change the independent variable. Okay, as you vary the independent variable. So they already given you the graph kind of plotted out with the points and the labels, and that's why the marks are not a lot. I'm not entirely sure how it works in physics, but I know in the older paper 5 papers for chemistry, it used to be like 4 or 5 marks where they just give you empty graph and you need to come up with everything from scratch. Okay, so that took a lot more time, But even despite this, it still takes time, so I highly encourage you to actually practice doing it, okay? So I have my value on another piece of paper because I can't bother flipping back and forth. Well, let's get started then. So 0.00292, 0.00292. So first thing with this kind of graph is you need to think about what each of these actually means. So this is 0.005. So each of these is 0.001, 0.002, 0.003, 0.004. So what I'm looking at is 0.00292. So that is close to 0.003. 0.003 is 1.2. 0.003 is 1.2. So it's roughly there. Maybe I draw it a bit better. 0.003 and 1.2. And then 0.00585, give or take, is 0.006. So 0.006 and 2.4. 0.006 and 2.4. And then 0.009, which is 0.00877, rounded up, because it's almost impossible to get that precision on this graph itself. Yeah, it's easier to look for 0.009 and 3.7. 0.009 and 3.7. So now you 0.012 and 4.7. 0.012, 1112 and 4.7. Is that right? Yeah, 4.7. And then 0.0175. So this one is an exact value because this is 0.015. So 0.016, 0.017, this is 0.0175, exactly in the middle. So 0.0175 is 7.3, 7.3, so 7.12 and 3. And then 234, I would imagine that would be close to 235. So 234 and 9.7. 234, so there's 1, 2, 3, so there's 0.023. You gotta realize that this is 0.024 there, so this is 0.0235, so somewhere in between there. 0.0235 and 9.7. 0.0235 and 9.7. 9.7 is there. And then 0.0351. So 351 will be close to 0.035, I would imagine. And that's 10.4. 10.4. 10.4, 10.4, 10.4. Am I correct? 10.4. Yep, okay. And then 0.0468 is close to 0.047. So that is 0.045. So 46 and 47. 47. 045. 045. 046. 047. Somewhere there. Give or take 10.4. All right. Cool. So I've gotten what I needed. It seems that if I zoom this out a little bit smaller, it seems that well, obviously when you have no barium hydroxide, then you would not expect any temperature rise at all. So I know this graph will cut through 0, because when there is no barium hydroxide added, there is no neutralization. Therefore, the temperature is just the temperature of the acid, right? Because you dip the thermometer inside the solution containing the acid, then you add the barium hydroxide. So it's got to cut through 0. I can see, oops, sorry, that's too small. I can see that it's going to look like that. And then there's a constant line like this because the temperature flatten out because it has a maximum temperature rise, then it doesn't go any further. So I need to try and draw a straight line first of all. So I can do this on my screen fairly easily because, well, you know, that's the beauty of working on the screen. So you see, you want the best fit straight line, but that doesn't matches all the points on top. So I think that is the closest I can get to as many points as possible. Not really, because you see this thing here, I think I've done a mistake. It doesn't cut through 0, 0 now, so that's no good. I'll start again. So let me start. That's no good either. This is actually harder than I thought it would be. It's actually a lot easier if you have a ruler, then you can play around with it. Okay, so I think that is the best I could do. And then what I will do later on now is to join a horizontal line. Is that the best I could do? I could do better. So we know that it cut through 10.4, right? So if I just kind of draw this straight line first, and that's probably as straight as I could get it to be on my screen. So that's where they cut through, because this is a constant point. And yeah, I think that's it really. So it's draw two lines of best fit on your graph. Rather than trying to draw a curve, it's actually draw two lines of best fit. State the value on the x-axis, so you need the thing on the x-axis at the point of intersection. So not the y-axis, but the x-axis. So what was that? There's somewhere there, and it's the, I would say it's roughly the first square of that thing there. So it's here, and then the first square there. So we're looking at that. 0.021, 0.022, 0.023, 24, 25, 0.0255. So 0.0255 is the value on the x-axis at the point of intersection there. Okay. So use the value on the x-axis at the point of intersection. Calculate the concentration of the hydrochloric acid in mole per dm cube. So to do this question, you really need to think about the equation, the balance equation. So the HCl, so you need two of it because barium hydroxide has 2 OH minus, and that will give you BaCl2 plus H2O, and you should get 2H2O. All right, so the ratio of HCl is to the mole ratio of barium hydroxide. You will have known that I like to use fractions like this after I stated them out very clearly like this, because it's just my way of bookkeeping, and I've always maintained this method throughout my calculations involving mole ratios from paper 1 to paper 2, 3, 4, and 5, and this is the usual way that I usually teach students. Because for me, when I write them out clearly like this and set them up like this, there's almost no way it can go wrong, okay? Unless you don't know what you're talking about. Balance equation, 2 mole of HCl reacts with 1 mole of barium hydroxide. And how much volume of HCl do we use? Well, there is 60 cm cube of hydrochloric acid. So there was 60 cm cube of HCl. 60.0 cm cube HCl, and we want the concentration of the HCl. So all we want is the concentration of the HCl. So if I set it up, the square bracket refers to the concentration of the HCl. This is in mole per dm cube times the volume, change it to dm cube, divide by 1000, and then at the bottom, the mole of the barium hydroxide used was the x-axis, the mole of barium hydroxide added from the point of intersection, 0.0255. Oops, nope, I don't want that. Nope, okay. 0.0255. So that is all set up nicely. The concentration of HCl will be 2 times 0.0255 divided by 60.0 times 10 to the minus 3. Put it into your calculator, and I get 0.85. That's what my calculator showed me. But I guess to be consistent with what I've written down from there, as well as the volume of HCl used, which I think was 3 significant figure, 1, 2, 3 significant figure, and my intersection point was 3 significant figure as well. So what I'll do is, instead of leaving it to 2 significant figure as my calculator show me, I will write it to 3 significant figure, because this is what we call appropriate number of significant figure as required back in your chapter 1 syllabus from the Cambridge curriculum. Okay, so next bit, explain the variation in temperature. So you need to explain it when you add barium hydroxide to the hydrochloric acid. So the graph has two parts of it. Okay, so there's the first part, and there's the second part when the temperature rise become constant, where there's no further change in temperature. The fact that we get a temperature rise, as I mentioned earlier, is because this is a neutralization reaction. So the neutralization reaction is just H plus OH minus, so it's just the recombination of oppositely charged ions, and you are not breaking any bond. In fact, you are forming hydrogen and oxygen covalent bond. So enthalpy of neutralization is always exothermic, okay, never ever endothermic. When you think about the ionic equation, they represent any neutralization equation, right? So initially, so meaning at the very beginning, as we add more barium hydroxide, so when you add more and more barium hydroxide, the temperature rise, which is the y-axis on the graph that we just drew, temperature rise or temperature increase. Temperature rise is the value. Okay, so that is the noun itself. The temperature rise increases in value. Increases in value as there are more OH minus that neutralizes the H plus. So obviously the more water you form, the more H2O molecule you form, the more heat energy that the reaction will release. All right. So after all, so because you have a fixed amount of hydrochloric acid, okay, you have a fixed volume of hydrochloric acid of a specific concentration. So after all the H plus have been consumed or neutralized in the technical term, that means no more H plus. So any extra, or you call them excess barium hydroxide added will have no effect, will have no further effect on temperature. And the reason for that is because there's no more H plus to form H2O with the OH minus, so the OH minus just remain as it is. All right, so no more water being produced, no more H2O is produced. If you don't produce any more H2O, therefore no further change in temperature, meaning no further temperature rise. Okay, no further change in temperature, therefore temperature rise become constant. Okay. Next bit of the question: when the experiment is done in the way described, the results are not very accurate. So this is to do with accuracy. Apart from the limitations due to accuracy of the measuring equipment, so you can't talk about using a better equipment that can have lesser number of error, because there's already said apart from that, okay, other than that, except for that, suggests. So a lot of these are higher order thinking questions, so you need to be ready to think through your practical experiments. Yeah, all the temperature rises are less than the theoretically should be expected. So this reaction releases heat, but what you actually measured is actually lesser. It's not as high as it doesn't go to as high as what it should be on paper theoretically. Okay, and because this reaction release heat, I can be thinking about heat loss. All right, so that means if my reaction loses heat to the surrounding, not all the energy goes into heating up the solution which contain water. So obviously we don't measure, we don't see on the thermometer as high as possible on the thermometer reading, because some of the energy is being lost to the surrounding. So you can think about heat loss. to the surrounding. So your surrounding consists of air as well, like gases in the air. They can get warmer as a result of the energy being transferred to them, okay, such as your air or your gases, all right? So, i.e., not, as I mentioned just now, not all the heat released by the reaction goes on to heat the water or the solution. So your acid consists of water. They are dissolved in water, right? The same goes for the base, is dissolved in water as well, obviously, yeah. And of course, once your barium hydroxide dissolves in the water, it's soluble. Okay, so why the temperature rises are more inaccurate as they approach their maximum value. So as you go higher and higher, so the reason why you approach a maximum value is because there's no more temperature rise, right? And that's because the reaction is nearing completion. So that means the H plus is slowly being used up already. So the reaction will be slower. The reaction is slower as it approaches the maximum temperature rise value, because that means it's working as much as it could already, and maximum temperature rise value. So what we could say is that because the reaction is slower than, so the heat loss is a lot greater. Heat loss is nearing the maximum at that stage. Okay, as a result of that, so your value on the y-axis, which is the temperature rise, become more and more inaccurate as it approaches that maximum value. All right, so as a common thing when you have calorimetry kind of experiments which releases heat energy or which absorb heat energy, you want to minimize this energy exchange with the surrounding air. Okay, because gases can get warm up, gases can be cooled down, and you want to minimize that. So one of the improvement that is very common is you just use a lid. You use a lid to cover the polystyrene, or what we call the styrofoam cup. Okay, I think they call it polystyrene cup, but you might have heard of styrofoam cup when you did your practical experiments. Okay, there's one thing you could do. Another thing you could be thinking about is that I think the barium hydroxide was supposed to be added. You see, the barium hydroxide is added as a mass because added as a solid. Sorry, so it's a solid there. So in order for the temperature rise to be as accurate as possible, you want the reaction to take place fairly rapidly, okay? Because if you have a huge chunk of a solid, it's going to take a while for the acid to get into the inner part of the solid chunks that contain the barium hydroxide. So it's better if we crush up the solid barium hydroxide to make it into a fine powder, so that we get a faster or rapid initial rate, and this will give us a more accurate maximum temperature rise. Okay, so you can say, or crush the solid barium hydroxide, use to maximize surface area. So as you know, surface area can affect rate of reaction. So maximize surface area for rapid or fast initial rate of reaction. And when you have fast enough, and you can get a much more accurate representation of the temperature rise, right? So this is the last bit of this data analysis question, and it's worth 3 marks, so quite a lot of marks. This is about, instead of using hydrochloric acid, you use ethanoic acid. So ethanoic acid is a weak acid, hydrochloric acid is a strong acid. So this is back to your GCSE or IGCSE or O-level understanding of acid versus bases. And we're talking about that they have the same concentration, so we use the same concentration, but you want to draw on your graph another pair of line. So you need to have two best fit straight lines again, what you would expect to obtain, all right? And you gotta explain the answer. So before we go about it, let's think about the weak acid versus the strong acid. So the weak acid, this also give you only one H plus per molecule, just like HCl only give you one H plus per molecule. All right. Obviously, like because they have the same concentration, and this give you one H plus and this give you one H plus, the equation that you could write, I guess, CH3CO2H plus barium hydroxide. So as I mentioned, you have two hydroxide, you need two of the ethanoic acid because each of these only give you one H plus. Since you have two OH minus, you need two H plus in order to balance out the formula, just like that. So it's not different from what we have shown with 2 HCl and giving you BaCl2 and 2 H2O. Okay, so the mole ratio is exactly the same, and therefore since the mole ratio is the same, and also we have the same concentration of ethanoic acid on paper, based on the equation, all right, based on the equation, so the mole of acid reacted, actually the mole of ethanoic acid reacted, is equal to the mole of HCl reacted in the previous equations. Therefore, no change in the mole of barium hydroxide required for neutralization. Okay, required for neutralization. So meaning to say the intersection point, at the intersection point, the x-axis value will not change. Okay, so no change in the x-axis value where the new lines intersect. So definitely we have new lines because this relates to the second part. So that was the x-axis doesn't change, but then the y-axis to do with temperature rise, and because we have a weak acid, so a weak acid like ethanoic acid only partially dissociates, or we call them dissociates into, well, dissociates or ionizes. Actually the other word is ionizes. You should choose one, but know that both of them have the same meaning. Okay, ionizes into H plus in solution, whereas a strong acid dissociate completely into H plus in solutions. So therefore, not as much H plus compared to same concentration of HCl. Same concentration of strong acid HCl in solution. And as a result of this, if you don't have that much H plus, then you are not producing as much H2O molecule as a result of neutralization. So therefore, not as much H2O was produced, or is produced, I guess. I don't know about the past tense or the present tense. Anyway, that's not the most important thing. So I should probably write that better. Was formed or produced, I guess produced or formed due to neutralization. If that is true, then it will release less heat. Therefore, reaction here will release slightly less heat. So it is still exothermic because you are still reacting H plus with OH minus, but you will be releasing less heat. Therefore, slightly lower temperature rise. So your y-axis where they intersect will be lower. Okay, so going back to the graph, here you have something that goes higher like this, and that's the intersection point where the pink value is. What I expect is that it will be low, it will still be 0, 0, because when I don't add any barium hydroxide to ethanoic acid, there can be no neutralization, and therefore there can be no temperature change. but it will be lower, but it will still get neutralized at the same amount of barium hydroxide added because of the equation I just mentioned earlier. All right, so if I use a slightly, I already have blue there. This is a sketch, right? So I'll just sketch something out. I guess make my life easy, and so that you can easily see what is going on. If I just have any good old straight line like that, and then I can start from 0, 0. Doesn't matter because this is a sketch. So important thing, start from 0, 0, because when there is no base being added to the weak acid or strong acid, there is no neutralization, therefore no temperature rise. It's a weak acid, there is lesser H plus that it dissociates into in solution, and therefore lesser H plus mean lesser neutralization, extent of neutralization, because you have lesser H plus in solution, and therefore you don't produce as high of a temperature rise. In fact, I have made a mistake. It shouldn't be that. Remember that on our x-axis, it has to cut through there. All right, so I guess that is better, and I guess I can extend this a little bit. Okay, so that looks better. So important thing is that they both intersect at the same point, because they are both ethanoic acid and HCl are what we call monobasic acid, because each of them only give you 1 H plus per molecule. All right, so they cut through at the same x-axis value, but the y-axis value will be lower, okay, as a result of what I just explained. So that marks the end of this paper 5 tutorial.